force on a current carrying conductor. If a current carrying conductor is placed in a magnetic field, it is acted upon by magnetic force by which the conductor itself displaces from one point to other place, from one location to the other location. This is on account of the flow of charges in the conductor and the magnetic field. The interaction between the flowing charges or moving charges and the magnetic field, applied magnetic field. In the conductor, it is not one or two charges are flowing. It is a large number of charges are flowing. I say some billions or millions of charges are flowing. What are those charges? Those charges are free electrons. Free electrons are flowing in the conductor. Here the conductor showing the direction of the current, flow of current in the conductor. The electrons flow in the opposite direction of the current. This direction of current also indicates the direction of the flow of the positive charges. The flow of positive charges is similar to electron flow in the opposite direction. They carry same magnitude but different sign. One is positive, other is negative. The amount of charge, what amount of total amount of charge it is flowing while the current is flowing in the conductor. From the point of view of Lorentz equation, the force, magnetic force acted upon is this given by the equation, that is a charge, moving charge particle having the charge of q coulomb. That is, a q is the amount of charge the moving charge carrying and its velocity vector and magnetic field applied. If the particle carries q charge, this is the equation. What is the equation? If the particle is electron charge is E, we know the magnitude of E. It is 1.6 into 10 to the power of minus 19 coulomb, E value. Replace this by this. This gives force experienced, that is magnetic force experienced by the one electron in the conductor. But the conductor has no one electron, it has many electrons. How many electrons are flowing in the conductor? It is based on this equation. N into L into A. That is, N is number of free electrons in unit volume of the conductor. Number of free electrons in the unit volume of the conductor. Free electrons are the one which cause for the flow of current. That is electron density, free electron density. This L into A, that is the length of the conductor and area of cross section of the conductor. This product gives the volume of the conductor. This is unit volume contains n number of free electrons. How many electrons present in the entire conductor? That is n into L into A. Total volume is L into A and electrons per unit volume is n. total number of free electrons which present or which carry current in the conductor are NLA. For one electron, it is the force. For these number of electrons, what would be the force? That is, the force means, so it is total charge moving in the conductor. This is one into this. And the equation, let us go for some rearrangement of equation. We shall take out V from the bracket and put L into the bracket. L and V have same directions. Velocity and length vector. Then this is the way V stands for velocity of free electrons. Velocity of free electrons means it is a drifting velocity in the conductor. Remember, velocity of free electrons is drifting velocity in the conductor. So all these things already been dealt with. That is meaning of drifting velocity and number of free electrons present in the conductor, all has been dealt with in the previous class in the current chapter, current electricity. Substitute V as Vd, we get the expression of this term, and we know that this expression of term is also known as I, current strength in the conductor, current strength of the conductor, I. Now it replaces in the equation these terms are replaced by I equals, final equation we arrive at this equation. F is the magnetic force. Magnetic force, or it is also called as thrust. The thrust means it is a pulling force. It is acted on this conductor. It is both, what is that? A vector equation. It has both magnitude and direction. There are three vectors, force L and V. They have direction. Magnitude of this all depends on the magnitude of these quantities. Magnitude of force acted upon the conductor is, that is, depends on intensity of the, that is, current intensity, length of the conductor, and magnetic field of the magnetic field applied, intensity of the magnetic field applied. And the direction we need to understand in this interaction. What is the interaction? Interaction between the moving charges and the magnetic field applied. Direction of the force, which you understood using Fleming's left hand rule. Here says L vector and V vector are perpendicular with each other, and this vector must be perpendicular to this vector as well as this vector, and these two vectors are perpendicular. Here the diagram says that this is the L vector, same as the direction of the flow of current. This is the direction of the magnetic field, applied magnetic field, inward direction at all points. Uniform magnetic field is applied at all points, same intensity, same direction. And these two are perpendicular to each other, and the force must be perpendicular to these two. The perpendicular direction either towards left side or right side. That is the one decided by Fleming's left hand rule. What is Fleming's left hand rule? Left hand, stretch three fingers in perpendicular direction, and this forefinger indicates the direction of magnetic field. The middle, direction of the current or direction of the motion of the positive charge. This will indicate the direction of the magnetic force. In this case, we know the directions of two vectors. field vector and current vector. You have to hold your fingers like this and turn the hand so that these fingers known vectors getting coincided with them. That is a magnetic field direction inward, and there is a current. You have to turn the hand like that so that this is coincided. This finger is getting coincided with the length, and this is coincided with magnetic field in this direction. Then the force exerted that we need to that indicates the force direction. So this is how the force is detected. Direction of the force is left hand side. So left hand side means the magnetic force or thrust is pulling this line or a wire towards the left side. That is lateral shifting. It is also called as horizontal shifting towards left by the action of magnetic force. It is due to the interaction between the flowing of charges and magnetic field. Overall force F on this conductor is this one. So final equation is the one which indicates the direction of the magnetic force and magnitude of the force which will supposed to act on this wire or conductor or line due to the interaction between the flow of charges and charge while flowing, they are not getting deflected like free charge. The reason, the electrons or flowing charge will never come out of the material. They are always bound with the material during conduction. Bounded, the charges are bounded. That is the reason the effect, what is that? The deflection effect is in the form of force acting on the conductor, resulting for displacement from one location to other location. That is the force, magnetic force or mechanical force or thrust on the conductor. Equation for only a single conductor which is placed in the magnetic field like this. Here we have a conductor and applied magnetic field. And in the next one, here the diagram says there are two conductors and no applied magnetic field. There are current carrying conductors. How many are there? There are two current carrying conductors. Conductor 1, conductor 2. And no applied magnetic field. But no applied magnetic field. However, magnetic field are induced by themselves. Any current carrying conductor induces magnetic field in its surroundings. So this that is a conductor induces magnetic field in its surroundings. This conductor induces magnetic field on this conductor because it is in its surroundings. Similarly, and this conductor induces magnetic field in its surrounding and induces magnetic field on this conductor because it is in its surroundings. At every point of this conductor, let's see that at every point there is a magnetic field. What magnetic field? Magnetic field that is induced by this current, by this conductor. That magnetic field is called B1. At every point there is a magnetic field induced by this conductor. What would be the direction of the magnetic field? That is in accordance with the Biot-Savart's law. Biot-Savart's law, direction of magnetic field This is the current carrying conductor. Hold the fingers like this. Direction is inward direction. This line represents inward direction of magnetic field. B1 represents magnitude of the field induced by this conductor. At this point, that is a magnitude and direction. This inward direction means perpendicular to this inward like this. This is the current direction of the second conductor. And these two conductors carrying current I1 and I2, currents are in the same direction and they are kept apart and separated by a distance of r. And in a similar way, the magnetic field induced on this conductor is V2. At every point we have V2, V2, V2 direction. What would be the direction of the magnetic field? It is in outward direction. Perpendicular to the plane in the outward direction like this. Use the same Biot's law. That is the current carrying conductor like this you apply here. Here outward direction. At this point it is action like this, outward direction. Magnetic field at this point, let us call this as P1, let us call this as P2. Magnetic field at this point is V2 outward. Magnetic field at this point is V1 inward. Current strength in the conductor is I1, current strength in the conductor is I2. And distance of separation between them is R, they are parallel. They are in parallel and the current flow in the same direction. These two are there. Now with this equation, using this equation, one can evaluate and estimate what is the magnetic field induced on this conductor. Magnetic field here, sorry, magnetic force, this is magnetic force induced on this conductor. This is magnetic force induced on this conductor. Let us estimate what is that magnetic force that is acted upon or it is induced at this point. It is using the same equation. See that F21, I am writing this as F as F21, it is a force on the second conductor at this point. Let me take one point, any point like this, at this point, due to this conductor F1. The force at this point on this conductor, magnetic force due to this conductor, force on 2 by 1. You write this, what is that I? Current in the conductor is I2, length of the conductor is L, magnetic field at this point is V1. Same equation is written like this. And L into V1, write the definition for the cross product. L into V1 into sin theta. Look at the angle theta. What is the angle between the L and V? Length is in the direction of the current. This L and V are perpendicular. Theta equals 90 degree. If theta equals 90 degree, sin 90 is 1. Equation ready for this problem. Then I2 L into V1. What is V1? It is a magnetic field at this point. So how do you write the magnetic field? I estimate the magnetic field at this point using Biot's law. That is already taught. If the conductor carrying current, this induces magnetic field at this point. The point is on the conductor at a distance of r. The magnetic field, that is V1, is given by, what is that, mu naught I1. What is the current in this conductor? Magnetic field at this point due to conductor having this current, that is I1. Distance at which it is separated point from this conductor is P, that is R, 2 pi R. So this is based on the it is based on the Biot-Savart's law. B1 is equal to mu naught I1 2 pi r. It is the magnitude of magnetic field at this point that is needed. Substitute this and see the equation. F2 equals I2L mu naught I divided by 2 pi r. And take the L to the left hand side, F by L, and right hand side is this thing as I1 I2. What is I2? It includes both the currents in both the conductors. And 2 pi r is the distance of separation between the two parallel conductors R. And what is the force? Magnetic force. This is magnetic force. Divide by means magnetic force per unit length. So this is F dash. Magnetic force per unit length F dash equals this right hand side remains same. What is that force? That force is this force. Magnitude of the force or thrust at this point is this one. It is given by this equation. Magnitude. Then direction. Direction that is understood by Fleming's left hand rule. Apply the same. Fleming's left hand rule. That is the one. You get direction of the field, direction of the current, and the force. So this would be the force of the magnetic field. Magnetic force. Magnetic force. Direction of magnetic force. At this point. Similarly, if we estimate the magnetic force at this point using the same mathematical idea here, apply that what is the same mathematics, finally we get this equation. This is by force at this point, this is the force at this point, that is force on the conductor 1 due to conductor 2. Force on the conductor 1 by 2. What is 2 1? Force on the conductor 2 by 1. If you do so, mathematical evaluation, we get the same equation. But the directions are different. Their directions are what is that? Opposite to each other like this. That is towards each other. Force acting towards each other. Magnetic force acting in the direction towards each other. This results the attraction between the two conductors. There is attraction, force of attraction. If it is plus minus, direction opposite direction. So it is understood whenever two conductors, parallel conductors carrying current in the same direction, whenever two conductors, they are in parallel carrying current in the same direction, they are getting attracted, mechanical attraction, that is the magnetic force will attract them, they are getting attracted, that is the magnetic force will attract these two conductors. Then what is the other possibilities? If the currents are in the opposite direction, if the current in this conductor is this direction and if the current is in the opposite direction, what would be the directions? Same derivation get, what would be the directions? Directions like this. This direction towards this side and this direction in this direction. Means they are opposite direction. The forces will act in opposite direction. So if this changes into this direction, this changes into this direction, and these two conductors are getting separated, are repelled with a force. So whenever a conductors who are even parallel conductors carrying current in the opposite direction, they are getting repelled by magnetic force. So that is what we understood from this concept. The magnetic force on the current carrying conductor. If there is one, it is simply shifting. If there are two conductors like this, either they are getting attracted or getting repelled, depending on the current direction. Same direction getting attracted, different direction getting repelled. And using this equation, most important of this equation, using this equation, we have defined the meaning of ampere, that is definition for ampere. Here we really understood what is the meaning of ampere, 1 ampere. Use the equation, see what would be the definition of ampere. Write this equation, F by L. F by L, put L equals 1, in SI 1 meter is say. Put R equals 1, in SI 1 meter. And I1 equals 1, I2 equals 1. Both are same, 1 ampere in SI units. What is R? Distance of separation of the two parallel conductors. What is L? Length of the conductors. Assume that they have same length of the conductors. L. So it is understood, if exactly 1 ampere of current is flowing in these two conductors and kept apart at a distance of 1 meter, these two conductors exert the force of 2 into 10 to the power of minus 7 Newton per unit length, per unit meter of the conductor. Is it clear? If exactly 1 ampere of current flowing in each of these conductors kept apart at 1 meter, the magnetic force, of course attraction, what is that exerted will be 10 to the power of 2 into 10 to the power of minus 7 Newton per meter length. Because repeat this equation and put L equals 1 and I1, I2, 1, R equals 1, mu naught by 2 pi. Mu naught by 2 pi, the value of mu naught divided by 2 pi equals 2 into 10 to the power of minus 7 Newton. That is the meaning. The definition, actual definition for ampere is, it is the amount of steady current. Steady current should be a steady current maintained in each of the conductors, parallel conductors. Amount of steady current maintained in each of these parallel conductors, which are kept apart by 1 meter, so that the forces, the magnetic force exerted by the conductors would be 2 into 10 to the power of minus 7 Newton. That amount of current what is maintained is called as 1 ampere. I'll repeat it. It is a 1 ampere means amount of steady current maintained in each of the conductors separated at a distance of r would exert the force of 2 into 10 to the power of minus 7 Newton per meter length of the conductor. That is the meaning of 1 ampere, definition for ampere. So with this definition, this is their ampere definition in terms of force, that is current strength in terms of magnetic force that produced due to flow of current between the two conductors. So that is the meaning of ampere. This definition is important.